we were told to burn water bottles, or actually destroy, and the guy decided that burning it was the best way to get rid of them. So he covered them in diesel fuel, lit them on fire, and only the outer ring ones lit. The rest were fine.
Well, that sounds like the stinkiest campfire ever.
I don't know. There was no wind
I have
whatsoever,
heard
so it all went straight up.
I have burned plastic bottles that were empty but were, shut, so usually they wouldn't really explode, but they kind of pop open, sort of. And I remember my cousins telling me that one time they've put batteries in the fire and it would actually like shoot things off or something. One time they accidentally put like one of the larger batteries, I don't know, I don't remember my battery types very well. They accidentally put like
Yourself?
yeah, like a D-cell batteries inside of them, and so like blasted a hole in the side of their camper or something.
You should put 22 ammo in the fire, Kyle.
But what?
22 ammo. Just put like a brick of 22
A,
ammo in
that's
the
hard to
fire.
find. B, that won't do much.
They won't go off?
Oh, it will go off, but it just won't do much.
There's a bang.
Yeah, and it'll shred the casing, but I mean, it'll barely pierce your skin if you're standing on it. And if you're standing on it, you're more likely to get burned. What we used to do is take river rocks, a cold river, and throw it in the middle of a fire real quick, and they'd pop.
Huh. It's always fun to throw things in fire and see what happens when I was younger.
Yeah, Boy Scouts.
There we go. Okay, I wanted to cover how to build a kernel today. And so we got to get that started first because building a kernel is going to take a long time on this machine. I was halfway tempted to go drag in some other machine to do it, but that sounded like a hassle. And we got plenty of other things to talk about. So as long as we start building the kernel early, we should be good. So I wanted to run this thing, make menu config. Did I show you guys menu config early on to demonstrate that things could be modules or built into the kernel? No? Okay, maybe that was the last time I taught this class. Sometimes I get mixed up because I always teach standing in the same spot. Really, we had to change, or we did change the carpet color, change something in the room every time so I remember where I've been. I get a different rug to stand on depending on which class I'm teaching. Okay, so the configurer here. Let's go ahead and exit. You can see what happened. And it won't take forever this time. Okay, so to build a kernel, you use make, just like any other kind of program on a Unix system. And so make has a few different options here, including menu config. And each of these different ones, it'll build stuff. You just get source code. You don't get the menu config program, but it'll build the, when you download the kernel, I mean. But when you run make menu config, it builds the menu config program, and then it'll run it. And so then at this point, you can go through and select options. Okay, now it says Linux x86 kernel configuration here. So it's built us one that's appropriate for the architecture we're on. You notice, let's go ahead and get out of this again. Up here, we went ahead and compiled all of this stuff on our machine right here. And so this menu config program can be built for the correct architecture. And the assumption here is that we're going to make a kernel for the architecture that we're building it on. If that's not true, there's ways around that, but usually it is. The reason it could be different, suppose you downloaded the Android source code and were compiling a kernel for your phone or something, then you would have to build it for a different architecture. Okay, anyway, so we get to select whether we want a 64-bit kernel or not. Of course we do. And I think the settings in here, I think this, I don't know this, are going to be set up for the default options for Ubuntu. Because I installed this kernel source code from the Ubuntu package repository. Probably the more common way to do this is just go to kernel.org, and from kernel.org you can download whatever kernel you want. And so we could actually grab kernel 4.2.5 and install it on this machine. The odds are pretty good that there would be some sort of minor problem that we have to fix, and I don't really feel like fixing something like that right now. So we don't do that at this moment. Usually with a generic Linux kernel, when you put it into some distribution, it'll work good except, and the except usually means like the video drivers need to be reinstalled or something like that. And that's not a very big problem, really. Video drivers are not that hard to install. But you do have to remember you kind of give the operating system a heart transplant. There may be a couple of waking up issues. Okay, we'll use the same version for this. The reason that you want to do that is, for example, suppose you just don't like modules and you want to compile everything into the kernel. Okay, so options here. It's possible. Cross-compiling is what it's called when you're building a kernel on one architecture and you're installing it on the other, building a kernel for your phone situation. If we start going to that, we can, I don't want to run down that rabbit trail, but that's where you go. Okay, you can do other stuff. Swap, we can not support paging of anonymous memory. I'm not sure what the anonymous there exactly means, et cetera, et cetera. And so there's a lot of options on here that you might want and might not. I haven't built one for my own system for about 10 years, so most of these I'm not even familiar with anymore. Okay, let me go do some stuff that's, there's a RAMFS stuff. I've been noticing that in 0.11. Everything in here is still there. Okay. One of the reasons that you might want to compile your own processor type. So if you got some sort of processor that has extra instructions, you can enable them in here depending. Do you need support for each of this stuff? Most of these things that are getting common these days, like hyper-threading and multi-core, are going to be built in. We could dump out the Intel MCE features here if we wanted to, because this machine right here in front of me has an AMD processor, Intel laptop support, etc. Okay. On for a while there. Anyway. So device drivers, as I was mentioning, are common use for modules, and so a lot of times this is the reason I pull this up. For example, you can go to network device support, and we're going to see a bunch of different network devices here, and they're going to be compiled using modules. And we can choose if we want to do modules or not, but that's going to be the default on pretty much all of this stuff. Let's look for file system support. File systems. Okay. So you notice ext4 support is starred here. I haven't mentioned this, but you might have noticed up here, star means built into the kernel, and or it can be excluded completely, or it can be a module. And so if we, for example, wanted to not bother with XFS support, we would just go ahead and do that. And now we don't have any. If we want to build it straight into the kernel, like we want to boot from our XFS file system, then we can do that and boot it right there. And that works fine. Incidentally, these modules here on the file systems, this is a limitation on what the operating system can boot from. If the kernel requires loading a module, and the module is going to be stored in a file system, then things are not going to work right. And so if you want to be able to boot from a B3FS file system, you need to put a star there. Ubuntu gets around this problem by having a separate partition, a separate file system actually, to boot from. That's usually going to be ext4. I don't remember if I changed anything up there or not. Okay, pseudo file systems, things that are not really ones. You notice proc is built into the kernel, but if we want to, we can not have proc available on our kernel. That may cause a problem for any kernel module that expects to have it, but we can not have it if we don't want to. And so really when we're writing our kernel modules, and so we probably should be checking to make sure the proc file system is actually supported before we go ahead and use it. I've never seen a kernel that was actually configured without proc, but yeah, it's an option. Okay. So that's the basic setup on all of these changes. Now RAMFS should be in here somewhere. Oh, that's right, I put XFS into the kernel. Oh, they do it as a module. Okay. I was looking for RAMFS stuff. Miscellaneous file systems is in there. Amiga, BIOS, JFS. We don't like JFS. SquashFS. Squashed file system support. It's a compressed file system. Compressed file systems used to be kind of popular when hard drives and things were small. I used to use it on floppies, for example. Okay, TMPFS. I'll look for RAMFS. Maybe you can't even pull RAMFS out though.
Would RAMFS be like a TMPFS? Because that's just like enabling support for those kind of virtual.
Yeah,
systems.
it may just come in with that one. I wanted to build it into the kernel and not leave it as a module if I had the choice. But assuming it doesn't appear anywhere in here, then we're probably fine. We'll just leave her be.
So if you don't support the TMPFSs, then you can't do like RAMFS at all, right?
I wouldn't think so. Yeah. Virtual memory file system. Performing, yeah. Okay. So anyway, I've gone through and picked options and that kind of thing. Ubuntu supplied third-party device drivers. So this is part of what you get when you download a distributions.
RAMFS is good.
As an AUFS branch. Okay. So apparently it's a different way you can put it in there. You know, it clarifies that this is not selecting RAMFS versus not. This is how it's done. But I would say RAMFS is built into the kernel if this is. By the way, FuseFS stands for File System and User Space. It's a way to let users manage their own little file systems. Okay, so there's Uber Space Mode setting on. Yeah, by the way, there's when something's deprecated like that, it's going away. Remember it, because nobody appreciates it anymore. Kernel hacking. Print K and demessage options. Oh, you can choose to show timing information on print K. You can override, okay. Kernel debugging, memory debugging. Oh, what do we have in there? It's a few debug options. Okay, panic on oops. We can do it or not do it.
What's a oops?
Oops is a less severe problem than a panic,
Oh,
normally.
okay.
Unless you select that, in which case it's the same thing. I'm not sure they had oops in the 0.11.
Do they have a whoopsie?
I don't think so. I don't know the entire history of it, and sometimes these things move in and out. Allow GCC to uninline functions marked inline, in case it knows best. Remember, GCC knows best. Okay, cryptographic API. Okay. Anyway, so that's the basic point here. Let's go ahead and exit this whole thing, and I don't remember what we changed, and so I'll go ahead and make it. Oops. So when we hit make, it should start building the thing. Oh, there's an option here. Control C. J3, I think that's what I want. I think I might have got it right, so it looks like it's moving faster. Let's see. I see the webcam there. I see 3 megs, 4 megs. Okay, I probably made 3 children of the meg.
I'm guessing J3 multi-threads it?
Yeah, and it's usually recommended that if you're doing this, you include a few more threads than you have processors on the machine, because a lot of times they'll be waiting for I/O from the hard drive and that kind of thing. I matched it to the number of processors on the machine because I don't want the machine to get dog slow and the machine is busy managing the webcam. But anyway. Oh, I'm going to have a problem when I try to boot into the new kernel with the webcam. I didn't think about that. Solve when we get there. Okay, so it's working on it. I don't know how long it's going to take. This is a pretty low-end machine. Kernel has a lot of code, but once we've done it, we can make changes to the kernel and remake it, and we won't have to reapply our changes. Yeah.
Is there any way you could do it on your test machine so it doesn't mess up the camera?
So one over here.
Mm-hmm.
Yeah, if I have, well, I could log. I think I was testing with that one and this one actually, and yeah, that would work fine actually. And I just have to copy it over. And in fact, the kernel we built is generic enough that even though I'm about to reboot this Intel machine into Linux, it would work fine to move that kernel over here because it supports generic x86. Now, I didn't used to build my kernels that way because when I was running an Athlon XP processor, I would put all the AMD stuff in and I wouldn't bother with anything for Intel or like motherboard chipset support or any of that stuff. And so it became dreadfully unportable, but of course it was smaller. In this case, we got, I didn't go through all the chipset support, but we got support for basically any motherboard that's at least slightly common, or that any kernel developer has ever used. Okay, so that'll be a while, and that one will reboot, and eventually I'll walk over there and select Linux, possibly run over there, like right now. By the way, if you're looking for more of these keyboards, we got a crate of them.
Which computers support those? Because they don't all have PS2 ports.
All the Intel ones.
Okay.
What do you mean by looking for more?
Oh, well, if you're testing a keyboard interrupt handler, then you might want to use a PS2 keyboard so it actually creates interrupts on interrupt 1. And I moved the keyboard boxes over here, and so under the table there's boxes and boxes of them.
Okay.
Some of the keyboards in those boxes are USB, but a lot of them are PS2. I think that's R1C6, that one over there.
Just make it work for any keyboard like a real man.
Where's the keyboard?
Yeah, good luck with that, Kyle.
Okay, yeah, no, it'll work, it's gonna work.
Maybe I'll have to go check. Oh, that's the
Huh?
password.
I haven't even started. Be fine.
Warner. Okay. Hey, we've actually got the Linux headers. And they are current for this one. Oh, but they're just the Linux headers. Actually, I should probably update it first. Okay, I'll punch buttons on this machine just like every now and again, and it'll be ready to be our official test bed eventually. It's dreadfully out of date, and I'm concerned that if I end up doing it without doing the upgrade, the upgrade will have some kind of weird issue involving versions of stuff and modules that get loaded. Okay, so anyway, while we wait for all that stuff to happen, time to talk about the setup function in Linux 0.11. Okay, I'm actually going to gloss over a few details just because we haven't been making fast enough tracks on the book lately. Okay, so I bet you this one would build faster. Maybe it's not an FS. Oh yeah, we were looking at this setup thing, setup function. So where we left off last time was right down here with this setup. And I mentioned that this has to do with mounting the root file system. And after this thing is run, we have a root file system. Okay, so as far as where this setup comes from, if we look for setup, we find this syscall up here. And we're using the syscall1 macro, which arranges a system call that has a parameter here, a memory address. And that gets thrown and put into a register, and then the system call happens, and eventually the address is handled in kernel space. Okay, we followed a few of these system calls through, and so I'm not going to bother to follow this one through. I'll just show you where it goes. It comes out in inode.c, if I remember right, and a function called syssetup. The function is definitely called syssetup, and so if it's not in this file, then I just went to the wrong spot. I knew where it was this morning. It's over here. Maybe it's not either of those places. Sorry about that. Okay, looks like it's in, oh yeah, hd.c, that's right. Okay. So the hard drive, I mentioned before, it's a block device. Certainly is. And so this sys setup in the block devices area is called. And takes this parameter, it's a memory address, and we're calling it BIOS because it's information from BIOS, basic input output system, about our hard drive. Okay, notes about this stuff. Yeah, do that. Oh yeah, so the whole magic only works once thing. It mentions right here you can't set up the hard drive more than once, so I guess that would cause some kind of problem. And so the static incallable here, remember a static variable means that you only have one of them throughout the whole program. And so in this case, we're going to have one. It's local to this function. It's called callable, and it's being set to 1. And then down here, we'll say if not callable, return -1 and set it to 0. And this line only gets run once because we just have one of these things now and always. And so once we set it to 0, we can't get past this point in the function. So that's that enforces only calling this thing once. I'm not sure why Linus felt it was necessary to enforce that this can only be used once, saying he wrote the whole thing, but maybe he thinks he might make a mistake someday. We declare a few variables here, and then we have to go through the hard drives and set them up. So this whole HD info structure up here, this is coming from up above. The stuff is always so hard to see on the little screen. It's easy to find when you have a big screen. Okay. Go for it. Oh, it's actually defined in the header file. No, there it is. Okay. So we're making a struct, an HDI struct, and it depends exactly what's defined here. It can, for example, have 2 entries, 2 structures that are all full of zeros, or it can have just 1 entry of HD type. Okay. So the whole HD iStruct thing, this is just going to describe what hard drives we have in the system. And notice we're kind of limited to 2 because that's the biggest that either of these arrays gets to, regardless of parameters. And if you go down and look here, notice that this follows exactly. Because we say drive equals 0, we start, and well, drive is less than 2. And so we got drive 0 and drive 1 at most. And so that's how many hard drives Linux 0.11 supports. Okay, so we're setting over here. You remember the heads and tracks and that kind of stuff from before, and so that's what the 2 things up top are. And then we got a few other parameters that explain what exactly our hard drive is. Sectors for sectors. Remember that most on a real hard drive you actually have 3 parameters because you'll usually have more than 1 head, and so you have it organized by cylinder and head and sector. And so you need at least 3 there, and then the CTL, I'm assuming, has to do with controlling it in some way. But anyway, so put together hard drive info here. So you got enough info to work on a hard drive. And somebody else added this CMOS stuff. It's actually credited with it. Has his name up here. Drew Eckhard. Check number of hard drives from the CMOS. Okay, now, this term CMOS here. We got CMOS and we got BIOS. And CMOS is a type of memory. I don't remember off the top of my head what it stands for. But the settings in BIOS, the stuff BIOS has determined, is stored in CMOS. And so if you, for example, have a machine where you've overclocked it and you can't boot up into it anymore, and it's about 15 years old, so it doesn't have any of the modern safety features, in order to get it to boot again, you take a little jumper on a motherboard and connect a couple of pins, which temporarily interrupts power to the CMOS memory that usually comes from a battery, and that will set your settings back to defaults because you cleared the memory that BIOS has changed. Okay, so anyway, we're looking at CMOS. And the terms CMOS and BIOS, I mean, they kind of almost overlap here. CMOS is the memory that's storing the stuff for BIOS. Okay, anyway, that's the 2. Okay, so, and actually, it's kind of funny here. It looks like Linus is using the term BIOS, and the guy who added the other stuff is using the term CMOS. Like referring to the memory directly. Okay, so we query CMOS and figure out exactly how many hard drives are on here. And at this point down here, what we're doing is reading the partition table. And so we call this bread function. Stands for block read. Breed? B-read? I don't know. Looks like bread. Anyway, so this reads blocks off the drive, kinda. And there's actually a fair bit of stuff that goes on behind it. So it calls into something else. And that's the one on here? No, I forgot to. Let's see if I can find it easily. I think it's on the file system stuff. Okay. So there's a whole bunch of uses of it, and it's defined in buffer.c, I think. Okay, right there. And so what it's doing, this whole buffer structure, so the hard drive, everything is buffered on a hard drive. And that makes it so, you know, if you request a bunch of stuff from a hard drive, the user level, you might not be taking the input, the stuff from a hard drive and using it immediately. Might not have declared memory for it, you know, that kind of stuff. And so it has to be stored in a buffer somewhere because you don't want to query the hard drive over and over again for stuff out of this sector. And so there's a whole series of buffers available. And so this get block thing is actually going to have to do is get us a buffer. And so we read something into the buffer and we wait for it, and then eventually we return it. BH here is a buffer head struct. And I'm not sure that's defined right here. I think it's defined somewhere else. It's used a lot of times. Struct buffer head start. Anyway, doesn't really matter. Represents the start of a buffer. And so this get block here has to go find us a buffer in order to put all this stuff in. Okay. So I think that's actually in here. Okay, there's get block. And so it mentions up here that the function isn't very clear and that kind of stuff. So I'm going to go over what happens more than the code because he's right, it's not very clear. He uses a clever go-to loop involving a fair number of conditions that bring you back up here and whatnot. But anyway, what we're looking for is a buffer, and these are all held in a hash table. So this get hash table finds you at one. And so once there's a buffer, then we can read our block into the buffer from the hard drive and start to actually use those contents. Okay. So that's where we're getting all of that stuff. And, oh, it's rels thing, releases buffer. And so you see it in here a number of places. I don't know why it's called rels, but if we're done with a buffer, if we read a block off the hard drive, put it in a buffer, we're done with the buffer, we want to release it. And so that's what it does. And we actually panic if we're trying to release a free buffer. It seems like it would be easier just to say, well, we're not going to free that one right now, but that's not what we do. So, okay. Okay, so that's the general idea behind this bread function. Okay, there's also this LLRW block. I want to mention that one real quick, because this one gets used by bread. So bread, after it calls get block and it gets a buffer head, ends up calling LLRW block. And that's not even in here. Okay. So that's used a bunch of times right in here. I think it might actually be in the kernel and the block stuff. Yeah, right there. It's on flat. Okay. So this tries to read something from a block device. Basically, it makes a request. So then the request goes off to the block device, whatever it happens to be, and we get something back put into our buffer with the buffer head. We could go through the details of how to read something off a hard drive. It's probably fun. We've probably followed that rabbit trail plenty far enough. Oops. Okay. There is one in here I do want to mention at one point. It's in fs.c, and it's add request. Okay. Maybe it's not in there. Maybe it's in kernel. Forget where this stuff is. It's kind of spread between these two files. Okay, it's in here. Okay. So this is kind of a funny one. Basically, this function here, when we're making a request for some stuff off the hard drive, it depends on where exactly everything is. And so we got our hard drive there, kind of concentric circles. And so if we want things that are in a few different places on a disk, we want to get them in order. We don't want the head to jump around. And so here, when we're making a request on our block device, we have to put all of our requests in order. So all of this in order macro here is basically finding us the right spot in this list to put the request. And so we got a linked list right here. And so you don't need a C++ vector. You can just make a linked list like this. And so it has some kind of request, and it has a next pointer in it, linked list style. And so we're basically going to find the next spot and go ahead and patch our request right into the list as we go. Classic linked list. Easy to insert things in the middle. And so that way we can quickly build this whole thing up in order to optimize our search. And this is actually one of the things that was a problem for solid state drives initially, because file systems are full of this kind of thing where you make sure that you manage your spinning drive with heads in an efficient manner, which doesn't necessarily make any sense for a solid state drive. In fact, for a while they had trouble with the solid state drives. So the magnetic drive, it doesn't really cause a problem if you use the same sector and over and over and over and over and over. You never wear it out. And so, for example, on a file allocation table system, you're going to be using the area. I don't know where the file allocation table is, but normally they would pick an area that's going to be pretty fast to read off of. So actually, my guess would be the file allocation table is going to get stored at the edge, because the edge has a higher linear velocity, and you're going to be able to read stuff off it faster. And so this worked great for spinning type drives. Pick the fastest part of the drive and stick the file allocation table there. For a solid state drive, they initially had a limited lifespan and number of read and write operations. And so you put the file allocation table somewhere that's not even really a very good place to put it, and then proceed to wear out that part of the drive, which causes trouble finding the files. Anyway, so this is very much a spinning type drive algorithm, but it's there.
Now I see why I have to take physics.
What?
Now I see why I have to take physics.
Oh, yeah.
I don't, it's stupid, it should die.
I hate physics.
You like
And
physics?
it hates you too.
I
I
don't
don't stand under our,
It hates everybody.
Physics is fun.
it's to build up enough potential energy.
It's debatable.
Debatable. Okay,
It's
so
not that bad, actually.
I enjoyed physics.
I don't know if I show this to everybody or not. This is what the partition table looks like on the computer in this room. This is set up in a little bit of an unusual manner. And actually, it's got a bunch of unusable space, like 139 gigabytes. And I'm always struggling here with my 20 gigabytes because I don't have enough space. My guess would be this was put together on one size hard drive and then imaged onto a much larger hard drive in mass. But it would be kind of cool to have another 139 gigabytes on here for the whole video thing. Anyway, so that's a partition table. And here's why this space is unusable. The names over there, SDA 1, 2, 3, and 4. These represent partitions 1, 2, 3, and 4 on the drive. Drives are allowed to have up to 4 primary partitions, and as you can see, all of these are primary. And so we cannot have any more partitions on this drive. That's a little bit unfortunate, but such is life. Okay, and it can cause a lot of problems if you change that. I don't really recommend setting up a Linux file system this way. Here's what I would recommend, because I did it. Thought I was doing. Okay, so wait, what? How am I looking at? Did I go into the wrong system? Why do I not even recognize this? Microsoft Basic. Oh. Let's go to a different machine. Okay. Good. This one has 4 hard drives in it, and so I got to actually pick the right one, which would be dev SDH. Okay, so now there's this little tree here. I don't know why I don't have that little tree set up on my office machine. Probably because I figure I'll set it up if I ever need it. This machine has 5 partitions on it, which is noted as more than 4. And the way we do it is we have an extended partition in this area right here. So you got that dev SDH2, partition 2 on there, which it mentions is type extended. And then inside your extended partition, you can have logical partitions, as many as you like. And so with this kind of scheme, you don't really ever run into trouble. And actually, we could have probably made well, no. You can't make a logical partition inside an extended partition bootable. That's the constraint. I knew there was something there. Okay, these partition rules, these are old rules, and they still keep us constrained today. And this pervades multiple operating systems and that kind of thing. It's just kind of how hard drives are organized. And I don't think I have a machine that dual boots, except for the one in the room, which I just showed you. But you got the same kind of issue on any platform you'd have. Okay, so yeah, software is actually simpler. iSoftware has 2 hard drives on it, and so I've got the extended file system set up here again. All of the space is allocated here. This is the root of the system. This is a solid state drive. And so it's got the root there, and it's got a 6 gigabyte swap partition. And I probably didn't need to use a swap partition, but I did. And then what everybody's user data is stored on, I thought it was STB, but maybe it's actually STB. Oh, I didn't partition that drive. So here's a trick. You don't have to partition a drive. You can just use it. It's fine. It doesn't need to be divided. And so the reason that CF Disk, the one that manages, the tool that manages disk partitions here, was like, what are you talking about? Right up here. It's instead of using partitions at all, the entire thing is just formatted with an XFS file system, whole drive. And so it's this is one case where you don't want to follow the instructions blindly. It says use wipefs if it's unexpected, which is probably a bad idea. Okay, so anyway, that's another way to set these things up. So now you've seen a few different ways. And I have to say this is definitely my least favorite right here, where you've got all this unusable space. If we wanted to get that space back, the way to do it would be to delete the swap partition and make an extended partition right here, and then have all of that space available. In fact, I kind of feel like maybe that would be a really good demonstration of how to use CF Disk. And I think the odds of breaking this computer in some bad way are minimal, but not non-existent. Okay, one thing we do have to do is turn the swap off. Okay. So, which one was it? I forgot. SDA4, right? I'll just guess. Okay, no argument. Swap off, options, spec, device.
You could just do -A and turn off all swap.
Yeah, that's the only one we have anyway. There we go. So now if I run top up here, you can see our amount of swap is none. And so now, if we fill up our 8 gigabytes of main memory, which we don't appear to be doing anytime soon, we're going to have a serious problem. But, we won't. Okay. So now we'll go ahead and delete this thing. Delete, gone. Okay, now I noticed some other stuff changed there. Let's real quick do that again and see what changed. We got an unusable 1 megabyte up there. We got an unusable megabyte there. The NTFS system reserve partition here, where it's booting from initially, 104. And then we got an 85 gigabyte partition there. Okay, so let's go ahead and do that delete. And my guess is so the unusable turns into free space. Okay, now we've got all of this. We want a new partition. We want to do a logical partition. And we don't want to use the whole thing. We want to go ahead and replace our swap. In fact, I'm going to go ahead and replace it with 8,000 megabytes. Actually, we'll go 8196. Is it 96? I don't know. 8192. I think that's it. Power of 2. It doesn't really matter if we do that or not. Okay. So this becomes unusable. The reason is we can't make a primary partition there, and our logical partition is going to extend from the end of this until the end of the drive, but it can't go back and cover something else. You can't have any exclaves in this.
So is that 1 megabyte just like conventional then?
It's probably just aligning something on a track or cylinder boundary.
Okay.
Okay, and so yeah, we want to make a logical one there, and 135 gigabytes. Good. Okay. Now we'll go ahead and write. This might destroy data. Yes, I know. Yes, we were taking a risk. No, I'm not doing this on a Sopra. Okay, good. Now, let's take a look at fstab. So fstab is the file that configures file systems when Linux boots. And so you can see we got this this identifier here for ext4, and then we've got this other one for the swap. And it says swap is on dev SDA4 during installation. And this is a UUID. This is a unique ID for a partition. This is not going to really work here anymore. So let's change that. The old way to do this used to be to specify the dev instead of the UUID. And so you specify just like /dev/SDA5, which is where we put our new swap partition. So we'll just do that. Okay. Swap on dev SDA5. We'll do it. Now. Oh, it looks like we haven't reread the partition table on the hard drive. And so it's not really consistent with what is in the, whatchamacallit, thing we were just looking at, CF disk. Okay, we'll reboot the machine right near the end of class and observe that this is like changed when we come back up. If we come back up. We'll probably come back up. Okay, so let's see, okay, I need to make this big for a moment. This is the configuration on that machine over there. And so it's asking me a question. Oh, this is possibly an issue.
It's not recommended.
Yeah. Okay. Yeah, that sounds good. We'll just leave this alone. Yes. Continue leaving grub all alone. Good, good. Excellent. Okay. Hey, found Windows 7 and everything's on here. Good. Okay. We're probably not breaking anything major. If not, it's probably unimportant anyway. Okay. So, back to our little tour. Where were we at? Oh yeah, I wanted to talk about partition tables, and then I saw something that would make a great demo. And so I'll reboot that and see what happens later. Let's check on our compilation real quick here too. So the compilation is continuing. The nice thing about make is I want to put some changes into the kernel here once it's done, and then we can observe that we can actually change the kernel, which is going to be cool, besides just putting in modules. I realize the modules are welded into the kernel, but there's just something special about actually changing the kernel. Okay, so anyway, once that's all done, if we recompile this, it's not going to take a long time. Okay, and that's the one over there, which is updating to be our test bed, and we're good. Okay. Okay, so reading from a drive. I kind of glossed over that one already, and so my notes gloss over it again. It takes a fair bit of work to read from a drive. And so we have to do the mounting the root file system, which is actually the same thing that well, it's got a lot of the same process here that I have to redo on this machine in front of us. So the whole reading the partition table, let's go ahead and get rid of that one. Oh, it's down there. I don't want it to be down there. Like something that scrolls by, go down there. It can be a decoration. My mother-in-law likes decoration. Everything decorated. Decorate, decorate, decorate. Okay. All right. So if we look at this HD.C, now we were looking at the partition table right here. And so this is the code I need to run again on this machine. And gets called from setup, which only gets called once on Linux 0.11. So there is really no way to redo it on Linux 0.11. I'm betting there's a way on modern Linux, because there has to be. If we wanted to like completely remove that drive from its consideration and put it back, we could do that, but then we would have a problem because that drive has the root file system on it. So anyway, we go through the partition table here, and there's some possible problems here, but off we go. Oh yeah, one other thing. So it actually makes enough entries for I times 5 here. It comes out to the right number of primary partitions. I forget how exactly. But we got these basically an array of partitions on hard drives. And so then once we can see all the partition tables, we go ahead and call mount root. Okay, so mount root is mounted here. It's going to be in the file system, because this is file system dependent. So if I look for mount root in here, it's in super.c, and the super function. Okay, so mount root, we're going to mount the root file system on this thing. And there's a couple of different cases. The root device, for example, could be a floppy. And that's fine. We can have the root file system be on a floppy, but there's still a couple of special considerations that happen there. And in fact, there's special considerations if the root disk is like removed. It can have consequences for the system. Anyway, if you just take out a mounted disk that's not the root device without unmounting it, then it's like, whatever, that's not very good. But that's good, yeah. So if you have a file system on your floppy that's the root file system, don't pull it out. Okay, so we're looking through and pulling off the root inode ultimately. But in order to do that, we have to get the super block. So the super block for a file system gives you the basic information you need to examine your own file system. So in writing these file system functions, these are all written assuming that the super block is going to come in and be something that you can use for it. So if we look at inode.c, this is where we actually do everything with inodes, like read inode, if we want to read one of them. We're going to get an inode structure here, and the first thing we want to do is get the super block, and once we've got all the information in the super block, we can go ahead and read our inode. Okay, so we want to go look at what's inside a super block. So this super block struct, super block. Okay, it's probably actually defined in like a header file. And there's going to be a bazillion mentions of it because, it's used all over the place. Okay, so there's a bunch of uses of struct super block. I see it in a lot of C files here. I think it may actually pervade even this and be inside the include directory. Okay, there it is. It's in fs.h. This is the stuff that's exported from file system world to everywhere else. Okay, so what's in a super block? I'm assuming that n inodes is like the number of inodes that are on this file system, max size of it, buffers for it, inode that it's mounted at, when you mount a file system, it has to be mounted somewhere. You don't just get to mount it in the middle of nowhere unless it's the root file system. And so you'll have some kind of inode here, which is where your file system is mounted. And so that's available. You know, there's a time on here, weights, locks, etc. Okay, so this sort of stuff will actually vary a bit based on what kind of file system you're after. In Linux 0.11, there's one kind of file system, and so it's not really like, well, okay, for my superblock, I need this, that, and the other thing. It's just kind of, this is what the superblock is for anywhere in Linux. And so superblock, let's take a look at how it's used again.
What is dirt?
Dirt.
Yeah.
Probably indicates whether or not it is dirty, as in something's been changed that hasn't been written to disk yet.
Okay.
And so that's very important when it gets unmounted. So if I go back, okay, and I think last time I was just looking at inode.c, and we very quickly found a use of the superblock, and I don't remember what it was, like write inode, there you go, that'll work. I think it was read inode we looked at last time, but it doesn't matter. We're going to do kind of the same thing here. We're going to go get the superblock for that inode. And then after we've got the super block, we're looking at IMAP blocks and SZMAP blocks and that kind of thing to figure out which block. And then we can read it off of this device. So I haven't looked at how the file system in here works, so I don't quite understand why this equation is right. But the general principle here is we have an inode, we have the super block for a file system. And so from that, we can work out what block on our block device, like what sector of the hard drive, we need to read in order to get the file that's associated with that inode. And so that's the basic process here that's going to go on for a function like write inode. And you see the same kind of pattern in other stuff too. I gets inodes, get an empty inode. Okay. So you have an inode that has the information associated with some kind of file, and from the inode you can get the superblock, and once you have the superblock, there better be enough information that you can retrieve the file for the operating system, and then it can have its information. All right, excuse me, for the user. You are the operating system here. Okay, so that's what goes into the whole superblock system. All right, all that stuff is done. Take a little bit to get that machine set up to be our test bed. Oh, I wonder what. Oh well, we'll do that later. I'm wondering what the partition table looks like on that one. Okay, so there we go. That's the root file system and superblock. And I guess I just reminded you what an inode is again. Now, here's the odd thing about Linux 0.11. It seems odd to me anyway because this is not how it works currently. On Linux 0.11, there is more than one type of inode. And so you've got M inodes and you've got D inodes. And so if we pop D and go back here and look at fs.h, we're going to see that you got a D inode, like a directory inode, and an M inode, which I think is kind of used for about everything else. These have been unified. There's just like inodes now. Okay, but for a file, you got stuff like what's the size, what the group is associated with, is it dirty, that kind of stuff, and what device is the inode from, and so all of that stuff comprises enough information to go and let ls do its work without having to look up too much stuff, and also let the file be found as it needs to be found. Okay.